Hello again, grade 11s. In grade 10, you worked with vectors as displacements and as velocities. In grade 11, we work with three vector quantities: displacements, velocities, and forces. Forces are vectors too, so we can add and subtract them like we do with displacement vectors. Look at the two arm wrestlers here. Neither of them is winning. The two hands are not moving, and we say the two forces are in equilibrium. We can draw vectors onto their hands and add them together. If we put the two vectors head to tail, we end up with the zero vector. In force vector language, this means that the effect of those two forces is zero. Nothing moves. The forces are in equilibrium. The resultant force is zero. In the previous lessons, we worked with displacement and velocity vectors. We added them head to tail to form a triangle. We can do the same with force vectors. In this diagram, you see two forces acting on an object. We draw two vectors, F1 and F2, to show the forces. The object is the dot where the tails of the vectors are together. We can move vector F1 sideways, parallel to itself. We are not changing the direction or the length of vector F1. The resultant force that is marked R is the force we get when both F1 and F2 act on the object. It's easier to see how R is the resultant force if you copy F1 and F2 so that they form a parallelogram, like this. The blue vectors are copies of F1 and F2. They have the same directions and the same length, but we can redraw them here to form this parallelogram. Then we draw the diagonal of the parallelogram. This is again the resultant. It shows you the force that you get when the two forces F1 and F2 act together. Engineers often want to work out the forces that are acting on a structure to find out whether the structure is able to take the stress of forces on it. For example, if a car drives into a double-story parking garage, its weight exerts forces on the floor. You don't see the building fall down. In fact, you can't see any concrete move, but there are still big forces acting on the parts of the structure. We are going to the lab to do a classic demonstration that shows how forces on a body add together. When their sum is zero, they are in equilibrium, that is to say, nothing moves, even though there are forces acting on the body. Look at this forces board, which you might have in your school. At the top, we have these two pulley wheels. They spin freely. This is important because they must roll when the string moves even slightly. Here are the strings. They go over the pulleys, and these weights hang on the ends. We know what the weights are. This one on the left is 3 newtons, this one in the middle is 4 newtons, and this one on the right is 2 newtons. So we know what the forces in the strings are. We have a knot here in the middle. This represents a small body or object. Imagine this matchbox as the object. If the strings were tied to the matchbox, it would be as though the strings were all tied together here at one point. Then we can ignore the matchbox and just concentrate on the strings that pull on each other. In other lessons, you have heard about free body diagrams. Well, this knot is a free body. It will go wherever the forces move it. Look at this sheet of paper I have taped onto the board. It is here so that I can draw the position of the strings on it. Later, I'll take the paper off and the pencil marks will be the data we work with. Let's look closely at the forces acting here at this point. The mass on the string has a 3 Newton weight on it. The pull in the string is called the tension in the string. The tension is the same all the way down the string and all the way to the knot, here. In this string on the right, the tension is 2 newtons all the way, and the force in this middle string is 4 newtons. This 4 Newton force acts vertically downwards, towards the center of the earth. These two forces on the sides are not pulling directly upwards, but they are able to balance the vertical downward force. Let's call these forces F1, F2, and F3. We want to record them on the paper. Now I'll check once more that the knot has settled in the position that the forces have moved it to. The strings and the weights must not rub against the board because we don't want any other forces like friction to come in here and confuse the picture. Now I'll press the knot against the paper and mark its position. I'll also mark the 3 positions where the string crosses the edge of the paper. Now I have dots to join and I'll be able to record the directions of the strings. Let's take the paper off and use a ruler to mark the lines where the strings were, like that. And now we can redraw the diagram on the board. Now we have the directions of the forces. What about their magnitudes? Remember that a vector has both magnitude and direction. Force F1 was 3 newtons, so we use a length of 4 centimeters to represent 1 newton. So force vector F1 is a vector 12 centimeters long, because the force was 3 newtons. Force vector F2 is a vector 8 centimeters long, because it was 2 newtons. And finally, force vector F3 will be a vector 16 centimeters long, because it was 4 newtons. You must remember that these vectors are not pictures of the strings. They are arrows that show the magnitude and direction of the forces in the strings. There's one vector we must still draw. It's the resultant of vectors F1 and F2. We can't see it yet, but it must be there, because the knot did not fall down. There was a force that held it up, motionless. That force was the resultant of forces F1 and F2. It has to be exactly the same vector as F3, but opposite in direction. Remember, the knot was not moving. That tells us that the downward force was exactly balanced by an upward force. So if we add the downward and upward vectors, the sum of the vectors is 0. I've copied the downward force vector F3 and I place it over the resultant force, like this. I am adding these 2 vectors together. They are equal in length and opposite in direction, so the sum of the 2 vectors is 0. This upward resultant vector is the result we get when we add vectors F1 and F2. How do we add them? Here is F2. We can move vector F1 parallel to itself. We do not change its magnitude or direction, so it's okay to move it parallel to itself. And look, if we add F1 to F2 using the head to tail method, we get the resultant R. We get a closed figure, a triangle. Now we can check our addition of vectors in another way. Here are the 3 vectors again. If we take F1 and move it down here, and move F2 along its line of action, keeping its direction the same, we end up with this triangle. The triangle is formed by the 3 vectors, placed head to tail. The triangle is a closed figure again. We have added all the vectors and the result is 0 force. We know it's 0 because nothing is moving. There's a useful rule that says, if a number of forces are in equilibrium, so that nothing in the structure is moving, then they can be arranged head to tail to form a closed polygon. A polygon is a many-sided figure. A triangle is a polygon. A 4-sided figure is a polygon, and so on. Now let's think some more about the structure of 3 strings. Let's increase the weight on the right side string to 3 newtons. What would you see happen? You can see that the structure will not be in equilibrium if we add a weight here, but it can find a new equilibrium position. The question is, where will that position be? Here is the answer. And this is how you can draw the vectors. F1 and F2 are equal in magnitude, both 3 newtons but pulling in different directions, so that they give us a resultant upward force R of 4 newtons. Again, we can arrange the vectors head to tail, and we get a closed polygon with 3 sides. Right, and here is a final question. If we put 3 Newton weights on all 3 strings, what would be the angles between the strings? I know you can work it out, so I leave it with you. And that's all for this lesson. You may have found it quite difficult, but you can check out other videos in this series where you can practice more with vectors. Don't forget the task video. Also look at the Mindset website at www.mindset.co.za/learn. Goodbye.